to introduce Dr. Marybeth Brey. Sherry has a schedule conflict, and Marybeth and I go way back. I worked on her PhD project as a first job right out of my master's. So it brings me great pleasure to welcome Dr. Marybeth Brey to join us for this week's seminar. She's currently a research fish biologist at the USGS Upper Midwest Environmental Sciences Center in La Crosse, Wisconsin. She holds a BS from Central Michigan University, an MS from Eastern Illinois University, and a PhD in Zoology and Fisheries Science from NC State University. While doing a postdoc at Southern Illinois University, she began her tenure working on the behavior of invasive carps in the Mississippi River Basin. Since moving to USGS in 2015, she and her team has focused their research on invasive carp biology, behavior, control techniques that's applicable to management actions of silver, bighead, black, and grass carps. Now, Marybeth is the team lead for USGS research and development of underwater acoustic deterrent systems for invasive carps. She works closely with the U.S. Army Corps of Engineers to develop and deploy acoustic deterrent systems in the upper Mississippi River, also at Barkley Lock and Dam in Kentucky. And to give everyone context to this fisheries management issue, this is some of the most important freshwater fisheries work that's going on in North America right now, because if invasive carps get into the Great Lakes, there's going to be huge management implications. So Marybeth is doing some very, very important work. So if she ever manages to find free time, Marybeth enjoys hiking and road trips with her dog. So without further ado, let's bring Marybeth Brey on, Dr. Marybeth Brey, to discuss her topic, development of an underwater acoustic deterrence for invasive carps. And take it away.
Great, thanks, Aaron. Appreciate the intro and the support for the work. I think a lot of what I do gets kind of washed over by, and my internet's unstable apparently. Let's hope it works. You know, it gets pretty political in what I do, and we just try to stay focused on the research and provide the best science possible. So the work that I'm going to present today it's a big collaboration, mostly with the Engineer Research and Development Center of the Corps of Engineers out of Vicksburg, Mississippi. So Krista Woodley is my partner in crime in this. So you'll see some mentions of ERDIC throughout, and a lot of what we're doing now is a team effort. So I'm not sure how familiar everyone is with this issue. I usually assume that everyone has a basic understanding of it because it happens to come up in the news a lot. But I'll give you some basic background here on invasive carp and deterrence, and then kind of move into why we're developing underwater acoustic deterrent systems and what we've needed to do to get to this point. So invasive carps are 4 species that we're concerned about: bighead, silver, black, and grass carp. And they obviously use the rivers to expand their range and jeopardize native species along the way. They were first introduced into the US in the early 1960s. And then by the 1980s, 3 of the 4 species, all but black carp, had escaped or spread to local water bodies, mostly through flooding in the southern US, southern Midwest. And today, carp have spread throughout the Ohio, Missouri, Mississippi, and Illinois River basins and most of their tributaries. And fish migration techniques have a long history, from structural barriers, so concrete structures, to non-structural deterrents to try and deter fish. Usually the case is that it's native species and you're removing those things. In this case, what we're trying to do is stop invasive species while having only minor or no impacts to native fish. And so a number of deterrent technologies are being developed right now, such as underwater sound, carbon dioxide, electric barriers, bubbles, and then combinations of these. And so I kind of got thrown into this. I had no background of acoustics other than telemetry. And so this has been a definite learning experience for me, but I like the ability to work on invasive species and try and control those. So that's something I've always been interested in. So I'm going to focus today on the underwater acoustic deterrent system, which has been my task for the past about 5 to 6 years now. And so the concept of acoustic deterrence is that we apply unique underwater sounds. And in this case, these are sounds that we're having engineered and developed by ERDIC in combination with some that we have used in the past. And we want to alter the behavior of invasive carps. And the rationale behind this is carps have specialized hearing. So they're osteophysans. They have their swim bladder connected to their inner ear through the Weberian ossicles. And this specialized anatomy makes them sensitive to underwater sound and vibrations. So we're going to use that against them. Potential benefit is that sound may be selective or semi-selective to carp. And we may be able to deter these fish as we focus in on a range of sounds without impacting native fish migrations or having limited impacts to native fish. So our overall goal for the research is really to develop acoustic playbacks that alter invasive carp behavior in a predictable manner. So we don't want to scare them so they go in a direction that we can't predict. We want to basically make them turn around or go to an area where we can collect them, and then minimize the impacts to native species. And so one of the reasons that we're working on this, and some of the pictures that you see here, and I'll explain some of these later, is that we want to get to the point where we can put these in the water at a large scale and test them. And I'll go into more detail about our specific Lock 19 projects in a moment, but this right here is our sound bar with speakers, these Lubell underwater transducers here. And the bottom picture is just an image of carp movement. And the reason that we're doing these large scale experiments, one of them is something you may have heard of. It's been in the news quite a bit for the last 5, 6, 7 years, quite a while. And that's the Brandon Road multi-deterrent system. So this was part of the Great Lakes Interbasin study, and they came up with multiple possibilities for deterring carp. So this area, my computer, you can kind of see the inset on the bottom right there shows you the Chicago area waterway. And carp are currently just below Brandon Road Lock and Dam. So that is number 5 on this map. And the area between 6 and 5 is an area of lower densities of carp. And so at this location, they're proposing and now designing a multi-deterrent system to try and keep carp at that location. And it's a good system because this dam never goes into open river conditions or overtops. And so fish can only go through the lock chamber at this spot. So everything that we're doing is applicable to this Brandon Road multi-deterrent system. So lessons learned go right into this. They currently have acoustic deterrent proposed for the downstream location, along with a bubble curtain, an electric barrier, and then another acoustic deterrent behind that. So 2 components of acoustic deterrence, because this isn't a kind of a singular research path, are, there we go, the environmental acoustics. So this is the side that my partner Krista has worked on quite extensively. This is the physics. And that includes things like the wind wave turbulence, vessels and ambient noise, what's going on in the environment. As more barges go through, that increases the decibel levels and the variety of frequencies that fish are exposed to. Includes the substrate, the flow, the bathymetry. All of these impact how you would put sound in the water and how it would interact with that environment and move through the environment. And then temperature and pressure as well. And so these are all things that we have to deal with. We also have to take initial measurements or do some initial research to determine what a site, what environmental acoustics how that might impact what we put in the water. And then the second part of this is what I'm most interested in, which is the fish behavior and the physiology. So fish can respond in a variety of ways. They could turn around, they could stop and freeze, they could go through a deterrent. And a lot of that's based on their motivation, also their sensory capabilities. So carp are going to have a different sensory capability than native fish. And so we need to know what that variation is. And then do all fish of a species react the same way? So does size have an impact on how they would behave or their life history? And so these are things that we need to take into consideration as we design an acoustic deterrent. So I'll go through some basics of each of these. And we'll start with the environmental acoustics. The environment where an acoustic deterrent is placed will greatly affect the design and the design of the deterrent. And in order to achieve that desired effect that we want, we have to understand the environment. So here's a few examples of how the environment can affect the acoustics. And the first one is the upper left here. And that's an idealized example of transmission loss. So you have a source over here on the left where it's red. So in this case, it's 165 decibels. And as you move across space, you have transmission loss. And so as you're moving from left to right, the sound projected in the water, there's expected loss. We would expect that as you move further away. But there's also something that can be thought of as a Swiss cheese effect, which is the reflection and refraction of all of those sounds with each other, with particles in the water, with the substrate, create a kind of a matrix of decibel levels at different frequencies. And so you don't have typically a uniform distribution of the sound from a single source. And that makes it hard to kind of project one sound through the water. So then in the upper right, this is an example of Brandon Road Lock and Dam, where we were doing preliminary measurements here. So we would have a speaker at the star, and that would be transmitting a combination of frequencies at known decibel levels. And this shows the transmission loss, the decibel loss, as you move away from that speaker. And so as you can see, it's not a uniform distribution through here. And the one on the left is the low frequencies. And then the one on the right is the high frequencies. So not every frequency is going to have loss or transmit in the same way. So again, makes it more complicated. So the lower left corner, this is an example of ambient noise, also something that we have to take into account. So at a lock chamber, which is often where we're working, you have vessels, we have the lock operation, so the gates opening, closing. We've actually recorded frogs and different fish sounds. So freshwater drum are one that we hear often. And then the size of the vessel and how much is in it can also impact how the sound goes through here. So you have a large vessel and you have speakers on the bottom, for example, that's going to impact what gets to the rest of the water column. If it's an empty barge, that may echo up into the air. And so then you have human health concerns and considerations. And if it's full, you have a different kind of vibration and sound pressure in the water. So when we work on this from a research standpoint, building something in the lab and having it work there doesn't always translate to the same thing in the field. So it's really important to have a variety of scales when we're working on this. So I just talked about some of the environmental considerations. We'll talk a little bit about the physiology and behavioral considerations here. And we've done a lot of research in the lab and small ponds to kind of get background information on carp. So one of those is auditory evoked potentials. And this is basically connecting electrodes to the brainstem and having a brainstem auditory response. So exposing them to specific frequency decibel levels and then measuring their sensitivity to that. So just like going to have your hearing tested for you to have an AEP at the audiologist. So in this case, this is a paper that we put out in 2018 to reanalyze. This had been done before, but we thought that carp hearing was actually higher than reported. So it was reported up to 3,000 hertz, but we thought that it was higher. And so Brookvetter ran these tests and saw that bighead silver and common carp all were most sensitive to about 500 hertz. And so that's the 80 decibels here is what you're looking at on the y-axis. So you're looking for the lowest sound pressure level that they can detect a frequency, and that was at 500 hertz. And so this is their most sensitive range. And then Andrew Nissen from University of Minnesota Duluth worked on a study to add in grass carp and black carp. So the black carp are in the filled squares and the grass carp are in the open squares. And we assessed the top one is the sound pressure levels and the bottom one is actually the particle acceleration levels. So two components of the hearing, and saw that they were sensitive at a lower frequency. So about 300 hertz. So these are the types of things that we use when developing the acoustic signals. They also had less sensitivity at some of these upper frequencies. So we can probably use similar acoustic playbacks to target both or all of the species, but there may be some differences, and that we have to take into account. So the particle acceleration levels, so this should be moved down here, my apologies. That's the particle velocity component of behavior. And there we go. So there's the hearing, the decibel frequency level, and then there's the particle velocity. And that's measured in decibels relative to 1 square per 1 square millisecond. And they are most sensitive to particle velocities in the lower 300 to 400 as well. And this is most important at a short scale. So on a large scale, like a lock, particle velocity may not be as important because there's a lot of particles already there. So then we've worked on the behavior. Brooke Vetter, Kelsey Murchie, and Al Mensinger from the University of Minnesota Duluth worked at UMass here on the left to set up a behavioral experiment where they put speakers on either sides of a constructed wall here and evaluated the ability of carp to move back and forth when speakers were turned on either side of that. So they were able to deter them successfully with a complex sound or a broadband sound, but not for an extended period of time with pure tone. So single frequency, single decibel combinations. And then in 2015, we did a large study in Morris, Illinois, where we wanted to see whether carp would respond similarly in the field. There was a lot of issues with that. We had flooding that year. We actually lost the boat. We were out there 24 hours a day, so we were on a rotation. But we were able to deter silver carp at this location using 100 horsepower boat motor playback. And the rationale for that was we know carp respond to boat motors. They jump out of the water, silver carp do. So let's start with that. So we recorded the 100 horsepower boat motor. It had a Doppler effect. So the sound kind of comes up and then it goes down like the boat's moving away. And so that's the sound that we started with. And then we've been working in the flume at Erdick down in Vicksburg here. And so the bottom picture is kind of a heat map of the distribution of fish. And in this case, this is good because the speaker is over in this location here on the upper right. And so fish tended to stay away from that, this particular sound. And so we're using those sounds now as we move into these large field experiments, but continuing to go back and refine these engineered signals. And then the right picture, we'll see if this plays. Okay, and I don't think you can hear this, but pretty soon you'll start to see carp jump out. This is Emaquan Preserve. It's on the Illinois River. Watch this area here. Okay, so you start seeing carp jumping out of here. We had 2 pit tag arrays in these. We had speakers active in the left one. So we had this behavioral response, obviously could see fish coming out of here when we turned it on. I think we got 1 or 2 pit tags detected coming out of there. So our the number of fish that we tagged and were able to detect versus the number we know were coming out of there was very different. But we were able to move fish out of these areas, suggesting that we could have an effect on fish behavior in the field. And these are just a few examples of what we're doing. We have some additional field and lab experiments ongoing. The other thing that we need to know about behavior is from a field site is fish passage and movement. Do we know anything about the current movement dynamics of these fish? And at Lock 19, so this is Lock 19 example, in 2017, 2018, we do, and this is from a paper that we had, Andrea Fritz led, it's in Biological Invasions, put out last year. So the arrows pointing up are times when fish moved upstream through the lock, and then the arrows going down are when fish move downstream. So in general, the carp, and without going into a huge long explanation, we can chat about it later, but fish that they had taken from above the lock, put transmitters in, and then put below, were much more motivated to make a return movement up. And so to date, we've actually had some fish that have moved every year for the last 5 years downstream on their own and then back up through the lock. So they suggest that this is a learned behavior as well, and that they will do this year after year. We also see that native species generally complete upstream passage earlier than carps, earlier in the year, which may allow for us to operate a deterrent during the window when carp are most active. So bigmouth buffalo and paddlefish tend to move upstream sooner than the carps do. And this has been consistent now for our 2019 and 2020 data. So I kind of went through this already, but our goal is to develop these deterrents, limit impacts on native fish. We start with lab studies, move to pond studies, work on field studies, and now we're really on these large scale deterrents. And so this includes a full scale navigation locks, multi-agency support, engineering and design, permitting, and then getting to a technology readiness level of 7. And before I started this, I had no clue what that was. And so the technology readiness level of 7 is something that's actually developed with NASA and used extensively by the Corps of Engineers and those doing research related to technology transfer. And so a technology readiness level of 7, it needs to be tested in the field. And several of these deterrents are scheduled to be tested at or put in at Brandon Road Lock and Dam. So before the Corps will actually do that, the technology needs to be at this level 7, which means a prototype demonstration and desired deployment environment. In our case, that's at a lock. And that's essential for moving the technology forward and seeing if this technology is a viable option for Brandon Road or other locations throughout the Mississippi, Ohio, Missouri River Basins. And this could change if the deterrent is deployed at a new location or in a novel way. So there is a feedback loop here. Just because like acoustic deterrents in one location are at a 7, it doesn't mean that all acoustic deterrents may be ready for deployment. And then this, which looks extremely busy and chaotic, has been my life for the last year plus. And it is. And so this just illustrates the feedback between the research and development, the construction and the engineering and design. So we have all these costs and benefits, and they all feed off each other. And a lot of them are happening at once, but this is kind of the constant development cycle. So you have a risk in the design, you have a risk in the technology, you have a risk of the environment, and you have a risk of benefits. Are there going to be any? And of the cost, can you afford it? And so all of these things are weighing into how you develop the technology and whether it will be used. So with that, I'll give you the example of Lock 19, which I said I've been working on for the last year. And I'm just going to acknowledge all our partners in this. This is a huge partnership of state and federal agencies, numerous coordination meetings. It's been funded primarily through the Great Lakes Restoration Initiative with the idea that this can prevent or could prevent carp from moving into the Great Lakes. So that's why we're able to use funding in the Mississippi River for something related to the Great Lakes. It's also funded by Ecosystems Mission Area of the USGS. And we all were working together to accomplish a February 2021 deployment and run this system for up to 3 years. We also had the study plan in development for almost a year, reviewed by all partners, so that we could also move forward on the permitting, which was a huge part of this. So our field site, Lock 19, you can see the Midwest here. Here's the Mississippi River with all the locks. And so Lock 19 is located right here at the intersection of Iowa, Missouri, and Illinois. So we had the joy of working on permitting with multiple states because the state line actually runs down the middle of the lock chamber. So we worked with Iowa and Illinois on this, everything in duplicate, never a dull moment. And then you can see the Chicago area waterway, the inset on the right, which is where the electric barrier currently is. It's north by Lockport, and then downstream of that where the multi-deterrent system is going in. And so Lock 19 was identified as a pinch point to movement, upstream carp movement by all the states, the surrounding states. There were 4 criteria. So this is a picture of the lock approach itself. So 4 criteria for a study site. Those included a place where fish cannot pass upstream over the dam. They can only go through the lock. And so the dam is over on the right side here. This has never gone into open river conditions. There's always been a head height of, I think, 15 feet. So this met the criteria. There was also a lower number of carp above Lock 19. So there is spawning above Lock 19. There are adult carp there, but the numbers are much, much lower than below the lock and dam. And a study here had to be applicable to other locations and deterrents. And so in this case, it's applicable to Brandon Road and also other basins. There also had to be a moderate population of invasive carp below the lock and dam so that we were able to monitor movement and documented upstream passage of both carp and native species, which there are at this site. So our objectives for the study are to design, install, test, and monitor the performance of the uADS, the Underwater Acoustic Deterrent System. If you're interested, I can tell you the history of that name later. And that was in the downstream lock approach of Lock 19. And then we'll evaluate the effectiveness of the uADS to prevent upstream passage of big-headed carp, so silver and bighead carp, as well as grass carp, and then native species that were suggested by the state partners. We'll also assess the behavior of invasive carps and native species in that lock approach itself, and then monitor system performance, cost, and all those things for the duration of the research, which is proposed for 3 years. You may wonder how long something like this takes, especially when you're working with the federal government and a lot of state and academic partners. So this has been intense. We had an accelerated contracting schedule, installation schedule started back in January of 2020 with a design with the Corps of Engineers, which if we would not have done that, we never would have made this happen. And then we had our own USGS engineering and design contract go in March, and that would kind of finish off the design. So the Corps did the 35, 65, 95% design for the deployment, this system. And then we went in and monitored all the things that I talked about before, the the current underwater sound, the ambient sound, took measurements, got bathymetry, all of that. And then our A&E linked in the above water parts of this, the electrical, the monitoring, the cameras, and then all of the acoustic deterrent and fish monitoring infrastructure and sound monitoring infrastructure in the water. So we had that final design by August of 2020. It took us a while to award a construction contract, but by December of 2020, we had the notice to proceed for construction. And then our installation, I moved down to Iowa on January 3rd, and we finished on March 15th, which was the date that we had to be done because they were opening the lock again. So we actually deployed in February, mid-February, the actual system, but everything else, plus the 6 weeks of our testing, took us into mid-March. And then we started tagging fish and beginning this study in April. And the system's going to operate from March through December for 3 years on a 80-hour on, 80-hour off schedule. So that's to give us kind of a paired design, or we're going to use a time to event analysis to evaluate fish movement. And the design included, I'm going to go through some of these kind of quickly because I talked about some of them already, but these include data that we collected at this site. So we did sound mapping to quantify the acoustic energy resonance. That was from February through August of 2020. And so we'd project at, say, 100 and I think we're at 170 something decibels. And that dissipated by the time we got to the end of the lock approach. So we were able to do that. We got the bathymetry, which is on the lower right here. So we knew where these discharge laterals were. This is the downstream approach. The gates are here. And our system ended up going right here. So there's a discharge lateral there, which means the water comes up from the bottom and discharge into the lock approach. There's also a discharge in this case on the right, on the river wall. And this is Swiss cheese. So there's big 10 by 10 foot openings all along this river wall, making this a horrible location to monitor fish movement, but we don't have a choice. So we're making it work, and so far so good. Oh, this was just another example of some of the things we're dealing with when you have a tow come through or the lock opening. We have a lot of noise. And so the pink box here is actually the fish hearing, carp hearing frequency. So the box are the darker areas, the red and the purples are ambient sound that's louder. So a towboat coming through is actually right in the hearing range of carp. So that makes it a little bit difficult. Luckily, the draining the lock doesn't have a huge effect. That's in the lower frequency range. Opening the lock doors right at the lowest range of carp hearing. So we have a lot of ambient noise to deal with. And so here is kind of layout of the design. As I said, we put the underwater transducers. So this is one on the right, upper right here, made by Lubell Labs, and we took them out of their casing and had them installed in this frame. And then they were dropped in. See the bottom of the whole thing being dropped in this last discharge lateral here, and recess down so that we stay out of the way of navigation. So that was the major concern of the Corps, is that we cannot impact lock operations and we cannot impact navigation. And so we had one location that they would allow us to put, and so we recessed it in this discharge lateral. So installed completely in 3 months. Our design took 8 months. So within a year, we went from nothing to installed and operational in the lock. Well, that's interesting. Those pictures came up funny. So what I was hoping is you could see this whole thing, but here are the divers, the dive platform on the bottom, installing this sound bar. So the lock approach is 110 feet across. The bar was 106 feet. So as they were dropping this in, there was not a lot of wiggle room to be able to put this in there. I was actually standing up on the gates up here. watching this happen, and it was a little nerve-wracking. So we were able to get this in, 16 transducer array. We also have a control center, which in this photograph would be over here on the left. There's a trailer that runs all of our equipment. We have sound monitoring throughout the entire approach to monitor sound levels. Here's our transformers and amplifiers. We have fish monitoring, so hydrophones in all of the, or most of the ladder wells, sound monitoring hydrophones throughout. And everything was actually done in duplicate. So if we had something fail, we could switch to another system because we knew that we wouldn't be able to get back into here easily. And then also, there's our fish monitoring, our water quality. There's our ADCP, acoustic current, or acoustic Doppler current profiler to get discharge in the lock approach. So a lot of different measurements. Here's just some pictures of our setup. So there's the sound bar again being, getting that ready before we deployed it. Testing the system. Colonel Sattinger from Rock Island District, who came to unexpectedly to see our setup. Here we're testing the speakers to make sure that they're functioning correctly. We did the same thing after they were installed. And then testing all of our acoustic receivers before they go in. We have 2021, just some more pictures. Here's the, oops, my internet comes back. A giant crane there that was dropping this into the approach. This is another one of our designs to deploy the acoustic receivers. This is on the left, the inside of our trailer, so our operating station. And the water quality and water velocity that was being monitored. We have a real-time station just below this site where we can monitor flow with this ADCP. So this is an up-looking current profiler. So we'll get the current or the discharge at centimeter level measurements. So a grid of centimeters throughout that whole approach. And the idea is that we then correlate that to fish behavior, to lock passage, or to lock operations and vessel passage. We also have cameras monitoring the water surface, so we can get the surface velocity, and we use special software to get these velocity measurements as the vessels pass through. So this is a different vessel impact the flow dynamics in that area. And then our water quality monitoring, we have a multi-probe that does the temperature, specific conductance, pH, and DO. So tried to hit everything possible that could impact both fish behavior and the acoustics. And then we went ahead and tagged a whole bunch of fish. So some cool pictures on the right. This happens to be a silver carp right here, paddlefish. This is a lake sturgeon, flathead catfish, grass carp. And we used, if you're familiar, Vemco and HTI type. They're both a Novasi now, but both types of transmitters to get at fine scale positioning as well as large scale movements along the whole river. And we ended up with 351 carps tagged and 208 native species. And we've already had a redetection rate of those or detection rate after tagging of about 70% for both, which is really good. So we typically assume about 50% redetection in telemetry studies. So we were very happy so far with 70%. Unfortunately, I don't have any additional information for you. We're still working up the data right now from this year, and we're hoping to have a summary of that by January or February. And then kind of to finish this off here, we had a big, what we call party, because we were very, very careful, not allowed to do a lot in terms of interacting with our partners during COVID. So January, February, and March. It was also very cold in Iowa. And so when it came to June 3rd, we had a big partner and congressional meeting where we were able to showcase everything that we'd done. So here's my partner in crime up here on the right, Krista Woodley. And she's showing here our monitoring system for the acoustics. These are some of our state partners: Kevin Irons from Iowa DNR, Kim Bogenschutz from, or Illinois DNR, Kim Bogenschutz from Iowa, and then Teresa Lewis from Fish and Wildlife Service, and then some Corps of Engineers. And then my team, who is over on the upper right here, including our center director, Mark Akowski, and our communications liaison, Randy Hines. And then the rest of this awesome team who put in a huge amount of time, gave up parts of their life to stay in Iowa this winter. So none of this would be possible without them. We did record this as a virtual event, and we're going to send that out to partners soon. So with that, I guess what's next? What do we do? So I talked about this being kind of an adaptive process. And so here we have engineering and design component of this. We have the biological behavioral component, and then that feeds into management actions. And so we work very closely with management, which is really what I'm interested in, is applied research, to determine whether this meets their criteria for a successful deterrent. And that's a feedback loop. So this process continues over and over until we develop a product that's useful for our partners and has the desired effect. So if this were not to work, we would probably continue to refine it until we felt like there was a point when it wasn't going to progress any further. So with that, I'm happy to take any questions that anyone has. This is our picture after we had installed the deterrent. We were exhausted, as you can probably tell from my eyes anyway. And then our contact information down here. Oops, and go back. So thank you guys for paying attention. I'm happy to take any questions if there's time.
Absolutely. I think we have till 12:15. Anybody has any questions, feel free to speak up, or if you want to put them in the chat, I can read them out, whatever you prefer. Well, I'll start off a little bit of conversation. Marybeth, it looks like I'm doing some of the same stuff with multiple tag types on the fish that I'm working with, looking at 307 kilohertz and 69 kilohertz. What are some of the ranges that you've been able to detect in your study system? There's a lot going on, turbulence and acoustic, air entrainment, all this stuff impacting the transmissions and ability for those tags to be received by those receivers. So what are your thoughts on kind of the range and the use of these multiple internal acoustic transmitters?
Yeah, I was trying to see if I included a better map of the overall area, because I think that will illustrate. I'm going to say in a minute, but I didn't include one here, so I'll describe it. But yeah. So there's a lot of issues, and that's another reason why everything.
I hate to interrupt. I hate to interrupt you. We're can't really hear you that way. You sound like a robot. Try that again.
That any better?
Not really.
You can unmute. Let me see. It's just interacting.
It's the first time in the presentation that happened, so I'm not sure. I'll stop my video. I don't know if that would matter. Just plow through it, I guess. We'll try to pick it out.
I was thinking you unmute would help, but I'm sorry. Let me try one thing. Can you hear that?
Not really.
Well, I don't know.
Well, just go ahead. I can hear you a little bit. We might be able to pick it out, and if not, we can figure out plan B, or we can write out stuff in the chat as well. We have a couple other options, but I'd say just go for it and see how it goes.
Sorry about that. Trying to breathe. So yes, we've done a lot of categorized, so trying to do a postdoc area and determine what the range is near the lock. We have a lot of multi-path. So I've had to develop some internal USGS algorithms kind of to get at that. So the fine scale, we've been able to do really good within that lock approach because of our large number of hydrogels there. The memo lock is actually really good with pretty coverage. We've also limited the number of eggs and tight collisions with them type tend to cause issues. Have a lot of eggs, but we're getting downstream of the approach at about a half mile action downstream, and then upstream, and then in the lock approach did have a GPS right there, but the position on that really works. We were able to do zones, but not fine scale. So the HEI is complementary to that higher frequency, and then the tag height is different. So it's not the 7 and 8 pulses. It's unique and distance between the two pulses. And so that really helped us to find scale positioning. The combination of the two actually worked really well.
Pick a little bit out. Do you have 2 devices going by chance? Okay.
I can get back on.
How about we do this? Anybody who has questions, put them in the chat. We'll compile them and we will get Marybeth to answer them, and then we will send them out to the group or the individual who sent the question. So I guess Marybeth, you can try again, or Thea, what are your thoughts on this?
Yeah, I would suggest that she try to leave and come back in.
Okay.
And see if that, sometimes that fixes it. It's really weird that it was totally fine. And then right at questions, it went.
Yeah.
Give me a minute.
Okay.
So while we're just sitting here, that presentation was really cool. And what it does is it shows these very specific management scenarios that are super important even to ecological processes in other systems, because the background of this, for the folks that don't know, is these invasive carps, if they get into the Great Lakes at a strong population level, they have the ability to completely change the trophic status of the system because they're filter feeders. So what they do is they take out a lot of the plankton biomass that would be available to other fish populations and really have an impact to the entire system. Much like the quagga and the zebra mussels have done. You just add in another invasive to the situation and you could have big issues. Plus, I don't know if y'all have seen some of the videos of when an electrofishing boat starts or when somebody's just driving by in their boat and these fish just jump all over the place. So it's also a human health issue for just driving a boat through these systems. So yeah, they're taking a lot of the production and biomass out of these rivers and lakes, and binding it into these. Yeah, what is the budget for this project? It's got to be substantial whenever you're talking about USGS and okay.
Is that any better?
Oh, that is super clear. Okay.
All right, I don't know what happened, no clue, but
That's okay. Can you go back to my question about the 307 and
Sure.
69 kilohertz? Because I really want to have a conversation afterwards with you about this, because you're the only other person I've heard doing this type of approach.
yeah, and I think we're some of the only people that are working in the 307 kilohertz range because so our Western Fisheries Science Center has developed kind of their own coding or own analysis program for the 307 kilohertz to be able to triangulate fish and kind of come up with a model for weeding through all these millions of detections. And so we've worked very closely with them for the last 5 years, actually, to get to the point we are with the fine scale positioning data. And it involves a lot of work. So with that, we've taken a lot of done a lot of tag drags through the lock approach. So, we'll do 20 passes just in that little lock approach back and forth to get at the positioning where we are, known location with the boat, and then our tag, and then where does the software, where do we position it? To do a lot of that, and then refining of the model. And we've had really good luck so far, as long as all the equipment stays operational with that cabled system. We've just added in our HR3s set at 307 kilohertz too. And those have been good for presence absence. And we're trying to loop them into the 3D or 2D positioning, but I'm not as confident in that one yet, but we're getting there. And so that approach, I think we've had really good luck because of the amount of refining we've done over the last numerous years. The detection range on those is not as great because the way that we've tuned in the gains on each of those is really for a kind of small area. But we'll get detections. We have beacon tags out everywhere, so we know if a hydrophone is down. Every hydrophone is in duplicate in case a cable goes out or something. And our only issue is that you have those. We have a lot of this is true with the 69 kilohertz too. You have a lot of multipath. So you're getting that signal bouncing back to the hydrophone. And in some cases, we're only hearing that bounce back and not the first ping. And so we've had to weed through those a little bit. So that was a learning experience this year, working in the lock approach. The 69 kilohertz, Andrea Fritz's paper last year was based on the array in the lock approach that was all VEMCO. And she did VPS VEMCO positioning system or array in there. And the positioning of those was poor. So it was not great, but we were able to get it down to zones. So near the gates, middle of the lock, and then towards the end of the lock. And then detection range downstream up to a half mile or so, depending on discharge and conditions. And then the Upper Mississippi River Partnership we have VEMCO arrays throughout our hydrophones throughout the whole river. So then those fish, some we double tagged to get both, some we did individuals, some we did depth pressure. But because of the combination, we can also follow those fish throughout the rest of the Mississippi River Basin. So I think we've been happy with both approaches because each tag type gets a little bit different information. The detection range can be an issue. It's just taken a lot of work to get to the point that we have the coverage that we want.
Appreciate that. I really want to talk to you more about that. We won't bore everybody with all the little nuances of that technology, but as far as budget, we have a question in the chat. What is the budget for this project? And I suspect this could be up there.
It is, and I think people underestimate what it should be. They're like, you're doing research, it can't be that much. So I had an additional slide on this. So let me get my numbers up here. Because I get asked this, I don't know, frequently, but come on. There we go. So our total design and construction and installation. So that was from the core, bringing on all these contractors for the construction, underwater construction, divers, all of that was $2.2 million. The design alone was about $400,000. So that's from the Corps of Engineers. It's from our contractors at GEI and Bailey Edward. And then the construction and installation was the 1.4 million. So that was, and it's kind of stunk because we were in that time where everything was higher priced, right in the middle of COVID. And so the prices for steel were really high. Trying to get people on site was really difficult. Shipping things was difficult. So the cost actually went up. And so all of that development, installation, crane, that was the 1.4 million. Government furnished equipment. So other things that we purchased, like the speakers, the amplifiers, all of that, that was about 700,000. So in, yeah, adds a little bit to it. And then our annual operating costs are actually not much at all. They were less than $10,000 a year, and actually more like $6,000 compared to the electric dispersal barrier, which is up in the tens of thousands per month. So our operating costs are very low. We have about a $350 to $450 a month electrical cost. And so that doesn't really include all of our salary. So if I include everything, all the acoustic telemetry, the meetings, the 1 to 2 years prior of data collection, we're probably for 4 fiscal years around $8 million.
Oh, that's actually a little lower than I anticipated. But
yeah, we've done a lot. So.
Well, it's necessary work too. It's people see a big price tag, but the benefit would far outweigh that. You have another question in the box here, and it refers to your fish movement graphs. It looks like the paddlefish movement upstream doesn't overlap with the carp movement upstream. However, the paddlefish movement downstream may overlap with carp movement through the lock. Is that correct? And if so, are there any concerns of negatively deterring paddlefish?
Yeah, so that's a good question. And something that I didn't mention, and I should have, is I'd say 98% of downstream passage is over the dam, even with carp. So every now and again, we'll get a fish somewhere that I think we had 1 or 2 in the last 4 years that came down through the lock, but most of them go over the dam, and usually that's you know, it makes the most sense. It's the path of least resistance. It's probably a 10 to 15 foot drop over that dam, but that's really not much, and it's energetically less costly than trying to go through that lock itself. So we're not necessarily going to deter any downstream movement of paddlefish. And then the upstream didn't actually respond. From our lab test, we saw no response from paddlefish at all. They didn't care. But that's why we're testing them. They're a species of concern. So we want to put transmitters in them and see. Just trying to find my graph to make sure I come on the graph. Where did you go? Dun, dun, dun. There it is. Well, let's see if the share, oops, yeah. So, oh, I didn't share. Yeah, so we had, let's see, buffalo paddlefish were moving from about mid to late March through the end of late May. And that's when, yeah, carp were actually moving downstream then, and carp didn't start moving upstream until later in June. So that's why I was saying we could actually operate that deterrent we needed to, starting maybe in June, and actually avoid most of the native species upstream movements until bighead usually start before silvers around June 1st. And that's also been pretty consistent for us here. It's a little earlier in other rivers just because of temperature, but yeah. Does that answer the question? You're muted, Aaron.
Thank you. Tyler says yes, that answers the question. If anybody, so we're at 12:18 now. If anybody needs to move on, that's fine. Any students or faculty or anybody, any of our guests want to continue on the chat, we definitely have more time.